Hi, everybody.
Welcome, everybody, to Paleo Talks. This week, we are on episode 32, and we have Dr. Jim Mead with us. Hey, Jim.
How you doing? This is wonderful to be back with everybody and see people from Tennessee, and this is great.
So excited to have you on the show this week, and we'll get back to introducing you in just a minute. But we're coming to you from Johnson City, Tennessee, East Tennessee State University, and the Center of Excellence in Paleontology and Paleo Talks. And so what we'll do next is we'll have David tell everybody a little bit about the show and how it works. David, if you'll do that.
Sure thing. Standard format that we have worked ourselves up into by this point in 30 plus episodes of Paleo Talks. We're going to have our guest introduced here in a second, which should be a lot of fun. Blaine and Jim go way back, so this should be a fun conversation. Then we'll have Jim go through his presentation, and about halfway through the program, which will go about an hour, so about half an hour in, we're going to open it up to audience questions. So at that point, we'll remind our audience to start asking questions in the comments of the Facebook video. The second half of the program will be led by audience questions that we'll be reading out for Jim. And as always, if for any reason you can't leave comments on Facebook, head over to the Gray Fossil Site Twitter or Instagram account, send us messages or tweet at us there. I'll be keeping an eye on all the social media so we can catch as many questions as possible.
You never mentioned questions. No.
All of the questions.
And that it's being recorded and broadcast to the world, Jim.
I was told by a certain mentor of mine back in the day to know everything. So we're going to test
That's
that.
right. That's right.
I think Dick Mole said that. I never said that.
All right. Again, it's great to have Jim on the show. We also have Chris Widga with us, who will stay with us today and hopefully ask some questions along the way. As David mentioned, Jim and I go way back. Jim was my master's advisor back in 1994, the late Pleistocene, somewhere in there.
Yeah,
and,
memory goes quickly, Blaine.
Yeah, and David was also one of Jim's master's students, but many, many years later, and then here at ETSU. So best of friends and colleagues for a really long time, and hoping that continues for a long time further. And today we're going to be looking at Heloderma and the beaded lizards, which is so exciting. People that know Jim know that he loves lizards. And how many lizard shows have we had this on this show so far, David?
I want to say this is number one.
That is embarrassing, isn't it?
And after this, it will stay number one.
Yeah. Yeah, exactly. No, there's not a lot of people out there that are doing research on lizards. And so it's a really exciting group to hear about. And I love working on lizards too when I get the chance with Jim. But what we'll do is we'll move on into the show. Have you go ahead and share your screen, Jim. So as you start to do that, I'll keep talking.
Okay, so let me open up that and share screen.
So yeah, we've been colleagues forever and ever, as a lot of people that are watching today. And what we haven't ever heard from Jim on this show is your background in why you got into paleontology in the first place. I didn't tell you we were going to ask you this, but just sort of a through time, what got you interested in paleontology? How did you get to NAU, then ETSU, and now the Mammoth Site?
So I'll try to make it short and sweet and to the point. As a kid, my parents are zoologists. And but as a kid, they said, well, don't you want to read, novels and, things like that? And I go, no. And then I found a book on bison, and I thought, oh, that's so cool. And of course, I did a lot of field work with my dad. Of course, he was working on snails, which were interesting, easy to follow, easy to track down. And I just got more and more into that and got into archaeology like you did, Blaine, and Chris and others. And then I found that I didn't care about the cultural material. I wanted the dead things, the bones, the plants. So really in high school, working at the Arizona State Museum, it was just like, this is what I got to do. and I learned more and more about bones. And then at the University of Arizona, doing archaeology, it was kind of like, it's the bones that are fun. So kept going on that. What really cinched, I think, for me was a river trip down the Colorado River in the Grand Canyon in 1969, which is a long time ago. But it was with Paul Martin, Extinction's Paul Martin. And that cinched for me. I had to find stuff. And it was easy to find because all you had to do is climb and run and everything. So, I mean, that's what I did. And in graduate school at the University of Arizona up at Tumamoc Hill, which is the research lab, it was very active. All the graduate students there were publishing and helping each other, and it just became a family. And that's, to me, that's where it's all at.
And Jim, Paul Martin tells that story about that trip in the river with you in his, is it Twilight of the Mammoths? Is that what that book is?
Yeah, I think that's what it is. Yeah.
Yeah, it's great for anybody out there, sort of in the history aspect. You get to learn about young Jim Mead in the Grand Canyon.
That was in high school too. It's kind of like, and I was bald then too. That was so embarrassing.
And then you made it to NAU, where you had a lot of students that are out in the field now today.
Yeah, Larry Egenbrod was developing at that time, the quaternary studies program. And he brought me in because I had spent essentially 2 years at University of Maine. And he said, hey, I've developed this program. I want you to come basically run it and develop it. And let's pull all this together. And it's kind of like, oh, cool. We can do that. And it went from there. And everybody helped everybody. It was like Tumamoc Hill, except I was on the other side of the fence this time. I was the prof. And getting you there, Blaine, was a blast, and Chris Jazz and Chris Bell down in Texas. And I mean, just a number of people, it just mushroomed into something that's just fantastic. And although those were tremendous days, I feel that the good old days are actually right now, because these things coming back and doing more. And here at the Mammoth site, starting in 2016, it's been fun in retirement.
Mm-hmm. And then we hooked you in 2008 to come out to East Tennessee State University.
Yeah, you did. And that was fantastic. I would do it all over again. Going out there between 8 and 16. It was fun developing it. It was fun to see things grow. It's, as Arpita knows, being chair is the most wonderful job you ever hated, because it's a lot. It's a blast, but it's nerve-wracking, and
Well, thank you for all you did here, and we miss you here for sure.
Well, you guys are, all I did was open the door. You guys are going through and just making it what it is, and getting everybody there. Chris and Josh and everybody there, that it takes a team to do it. It's not a one-person job. And you guys are fantastic.
And now you're up at the Mammoth site and you're the director of research. And that's sort of a circle back for you from the 1970s.
Yeah, 1974, Chris, Larry Egenbrod and I were here, and we kind of go, yeah, it looks like there might be one, maybe 5 mammoths. Of course, now we have 61 mammoths.
Crazy.
But to me, I don't want to really, we're going to keep digging this sinkhole, right? But to me, it's not to find another mammoth. It's not quite one of those he who finds the most mammoths wins, because Dick Mole will always win with mammoths. Okay, so and that's fine. But to me, right now, I want to find more about what's surrounding the mammoths here at the Mammoth site, and that's looking at climate change. That's to me what's happening. And Kelly, who's on the list here, Kelly helped out by looking for more plants, and now we're doing isotopes. Grant, I don't know anything about isotopes. Chris, I can spell it, but that's about it. So, now we're just doing, the center bullseye of our research here is the Mammoth site, and then the next ring out from that would be, say, the Black Hills and some amorphous ring around the Black Hills. And then from there, it'd be Western USA, and then from there, international. So it's fun.
It's ironic to end up at the Mammoth site in many different ways. But another one of the reasons is because you push microfauna so much, and mammoths are not microfauna. And one of the reasons, that I went and was excited to work with you was because of that push to study the microfauna. The voles and the shrews, and then the lizards.
And the snakes.
And the snakes, and all of
and then
these
the
smaller
salamander and the frogs.
Yeah, all of these different animals that are telling the story. And so with that, let's start talking about lizards.
Okay. Well, what I want to do, as you can see from this, is I want to talk about Gila monsters, the beaded lizards, and the venomous side of it. Really, it's two main topics I want to kind of bring to everybody's attention, and I'm going to assume folks know nothing about this, okay? But I know there's a wide variety of knowledge here. I want to talk about osteoderms, so bone in the skin, okay? And then I want to talk specifically then about the Gila monsters and the relatives. Now, Blaine, I know you can read all this, and Davis, check my spelling on this. But no, what I'm really talking about here is this is the squamates. We know geckos, we know skinks, we know amphispenids and some of these other things. Here's the big group of snakes, right? They're really a lizard. They just, lost their legs. And then we're going to get down to some things, but well known to have dermal ossicles, osteoderms, will be a couple major ones. One would be within the skinks, okay? But then we're also going to get a bunch here in the anguimorph. Now, this is really what we're going to be talking about mostly today here in the next hour, is this anguimorph group. So know that term if you don't know it already.
So but for those people that aren't familiar, with what they're looking at here, this is a tree of relatedness. So those that are more closely related are closer together. And one of the things that I think is really exciting, if you're not familiar with this, is the fact that, again, like Jim said, snakes are a type of lizard, essentially. But you can see that snakes are actually more closely related to some types of lizards than what we would consider to be lizards are to other types of lizards that we would consider to be lizards.
Yeah. And as they do more analyses, whether it's molecular or morphological, which is what we're going to do today, or when you combine the two, this thing changes all over the place. It's a house of cards, really.
Which one's right, Jim?
The other one.
Okay, perfect.
Yeah. And so we're going to mainly look at anguimorph group, okay? And again, we're looking at things that have venom. So venom will occur in the snakes, as we know, and it will occur in anguimorph group. Down here, these are the anguids, which are the typical lizard you'd find all over Eurasia and Australia. And then this group down here is the typical lizard, all the iguanines that we would see in North America and all over. So we're going to concentrate on this group. And within that, I want to talk mainly about Monstrosauria. Okay, so that, I've kind of reduced it all down to mainly one area, but it's the osteoderms and the venom that kind of make it a very cohesive package. Osteoderms. Okay, so here we're looking at Gyrosaurus. This is a cool little lizard that's a skinkomorph. Okay, it's not an anguimorph, it's a skink like. But notice that the dermal ossicles are basically rectangular, and they're actually in the skin. It's not like Jasinski's turtles, where maybe the shell developed from the ribs and such. These are really dermal bone, okay, which evolves many times in many different animals. But in the lizards here, we're seeing it, and you notice how it's a complete armor. And as you go caudal towards the tail, this would be the head. This guy I broke off from here. As you get towards the tail, some of these dermal ossicles will get points on them and become rough or actually very pointed. This would be a belly, so it's nice and flat. But notice everything is pretty much rectangular and for the most part overlapping. Okay, they imbricate, which we'll see here in a moment. And then on the head, they fuse. They become a different shape, but on the head, they pretty much fuse together. So that's kind of a generalized thing that I want you to understand. Now, getting into anguimorphs, in North America, we have the alligator lizards. It's kind of a big group, and that group will go all over North America, right on down into Central America. In Asia, there's a relative of it called this big thing, Pseudopus. What's really cool, one of the many things that's really cool about the gray fossil site is you guys kept finding these little things right off the bat, dermal ossicles, and you look at it and kind of go, well, that's pretty, it's cute. Oh, I think the scale's wrong. This might need to be 5 millimeters, but anyway, it's itty bitty, okay? And you'll notice that there's this flat surface, okay? Now, remember I said they're all imbricating, so it allows the animal to move basically this way. And so that surface here is pretty much the same. But this ornamentation, this is the part that you and I would see. You'll notice in this case, there's a nice ridge going down it, and then there's all these radiating things. That's what we're finding at the gray fossil site. But if we were to go to the alligator lizards of North America, it's kind of like, no, nobody has that. None of them have that. They're typically very thin. They have some stuff on it, but it's kind of like, yeah, you're boring. You don't have this type of thing. So Blaine and Sandy and I are working up any year now, the manuscript, as soon as Blaine gets going, we'll work up what I think is, once again, a Eurasian and Asian type lizard occurring over here. I don't think this evolved into what we have here. Another
it's
story.
really interesting too, you know, when you see this, it's reminiscent of an armadillo osteoderm.
Yeah, it is. And that's dermal, you know. Now, as we all know that there's layers of skin, it's not just skin. So the layers of skin, you can develop bone in those different layers. And then of course the outer layer, you're going to develop a keratin. That's how we have fingernail, that's how we have hair, hair. And if you look at a pronghorn antelope, that horn develops at a different layer than the bovids, the bison, let's say. A lot of big story, a lot of go on forever on that. But I want you to get an idea that gray fossil site is going to be very critical to understand some of the things because of the osteoderms. So then we get into Varanus, okay? And this is a Komodo dragon, that's a croc back there. A Komodo dragon died at the reptile gardens here in the Black Hills. And they said, hey, do you want a Komodo dragon? And I'm thinking, oh yeah, I'll be a cute little baby that they got, and it died, unfortunately. No, it's basically 9 feet long. And it was the largest male Komodo dragon in North American captivity, okay? So it's kind of like, oh yeah, but it was frozen solid. So they stuck it in the back of the pickup truck, you know, and from about here out, it was sticking out of the back of the pickup. So it got a lot of attention as we drove it down. But anyway, if you look at the skin, you kind of go, well, it's knobby. I wonder what it has. Those are going to be the keratin covering, the scale covering that can do all kinds of things without any bone below. Okay, you can do all kinds of stuff with that horny layer. But what they're finding, thanks to Chris Bell working on a Komodo dragon, he CT scanned a large male. And look at these, all the white you see here these are dermal ossicles. That's not the square plate that we were just looking at. They're all elaborate, pointy little things. This really wasn't known for quite some time, really, what's going on. Notice in the head, they are kind of little nubbins, but there's areas in between. So variety, okay, that means it's morphologically identifiable. Now, when you macerate this animal, or let's say decay it down in a fossil, all that stuff will break down and all these things fall off to the side by themselves. So as a paleontologist, you'd go, oh, hey, I got a big jaw. That's so cool. What's all this other stuff? Oh, well, I'm not even going to look at that because it's small and I'm not going to work with it. Yet, I mean, look at that. And then, so we need, as paleontologists, we need to do fine mesh screening and then look at that stuff, which means we have to know enough to pull it out of the sediments to say this needs to go to somebody who can work with it. Well, that's what Sandy has been doing. We'll typically screen wash cave sediments and everything else at about 0.5 millimeter, which I think you guys are still doing there at the Gray site. And with that, you find lots of stuff. Now, unfortunately, that slows you down. So you can't, quickly go through all the sediments. But this is data. This is telling us something.
This is extraordinary. Has it been published?
Yeah, I think he just came out with this. I'll have to double check, but he just came out with it.
I mean,
Related to this, though, good point. This is Lanthanotus, so it's another anguimorph. They're an itty bitty lizard, so it's not like that Komodo. Here's what they look like, and all these knobs here are the keratin expression, not necessarily with a bone below it. Okay, but these are little lizards, about something about like that, living in, as you can imagine, Borneo. Okay. But when he CT scanned it, and then, as you know, with CT scan, you can kind of quote, push the button that says, just give me different types of bone. And look what is happening. This was not really known. These are all knobs, not all that different from some of the ones we saw in Varanus, right, on the Komodo, but they're all over the place, okay? You can see all of this stuff. And so again, that's going to fall off in the process of fossilization, if you will. And so you and I are going to find the, the dentary and all the other bones. That's really cool. That's identifiable. And we as paleontologists need to start looking for that stuff. Now, you guys at Gray are doing that. Cool. And Sandy and I are doing that here. I say Sandy and me. It's really Sandy. I go, hey, dirt. And she goes, yeah, let me look at it. And then she's the one that finds it. So they are out there, and they are morphologically distinct in many ways. So now let's look at Monstrosauria. It is monophyletic every time they work with it, and it's changing all the time, okay? Monstrosauria is monophyletic. It's a clade, and it includes this guy and Primaderma and Gobiderma and Estesia, named after Richard Estes, Estesia, and Helodermatidae, the whole family. And then within that, you have Paraderma, Loasaurus, and Heloderma. So I'm not going to show you all these, but I wanted to give you a feeling of why this is a monophyletic clade, why it's pulling together, and what cool things you can do to play with it. Not my best photo. I take this right out of Randy Neidham's excellent article in 2000. Primaderma, Cretaceous. Some would say this is the oldest of the Monstrosauria. Every time a new fossil is found and you get different remains, you code things, you include things, this will change. But whether this is the first or the second makes no difference. It's old, it's really cool. It's from Utah, it's Cretaceous, okay, about 98 million. What you're seeing though, again, I apologize a little bit for the picture, but you're seeing a lot of dermal material here, okay? But it's hard to recognize. You see recurved teeth, that's important, okay? You can see a little bit of a flange on here and a little bit of indication of serration. That's important too. We'll come back to that. But anyway, this is a very early one. If you find you want to read a little bit about this and kind of go, well, that's kind of interesting. What should I read besides the 100 articles of Just Know Everything that it tells us to do? Is this JVP article, Randy Neidham 2000, okay? Now, Mark Norrell at the American Museum has done phenomenal things with some of the earliest lizards. He's not the only one. Susan Evans, of course, is doing a lot. But Mark found Estesia mongoliensis. Needless to say, it's found in Mongolia. Okay, Upper Cretaceous. He described it. He and others described it. You can read that, but you must read this one by Yi and Norrell in 2013 if you want to know more about this group. Tremendous background information in there. What I really like, and he chuckles a lot about, of course, he's getting a lizard eating dinosaurs. Kind of like, yes, get even while you can, because soon it's not going to be that way. Now, if you look at the jaw, here's the mandible, right? Here's the connection to the head. Long part of the jaw, if you will. and this break here, that's kinesis. So it's not just a jaw moving this way, it can move multiple different ways. A number of things do that. Mosasaurs do that, okay? So you get a feeling that there's a long face. And if you, here's a, can I show this? A Varanus. Here's another Varanus type thing. And you can, let's see if I can get
Hey,
this.
Jim, if you unshare your screen for just a second, then it'll show up larger.
How the hell do I do that?
Just move your cursor around till the share screen comes up at the bottom.
Yeah, there we go.
Just click on that.
Okay, I clicked on it.
And then does it say anything?
It says,
Like-
do you want to share?
You want to unshare? There you go.
Does that work? That shared it though.
David, help.
It's just me being me.
I think it will show up now.
Okay.
He's showing up. Once he
Oh,
talks,
there-
he's
There
there.
we go. So
There we go.
here's a Varanus skull. Not a real big one, not as big as Komodo, but you can see the long face to it. Okay, and in this case, this one has knobby teeth. It's Varanus anthematicus that crushes things instead of chewing them. But there's no dermal bones on it at all. Okay, so this is just what you would say is, well, that's just a typical lizard and all that. So the Varanids are typically that way. But we saw the komodoensis had it in the skin. I pulled the skin off. It's not attached to this, okay? The dermal bones aren't attached. That's going to become important. Now, let's see, I got to go back to
Share screen.
that one. Sorry, folks, this is all new to me. Do I just push that? What do I do, David?
Click on share screen,
Share screen.
and then you have to click on what you want to share.
I want to share that.
Maybe
Maybe
David has to do it.
You should be able to do it. Just select which window you want to share, which should be your presentation. And then there should be a confirm option. There you go.
There
There
it
you go.
goes.
Perfect.
All right.
I hear Wally back there too.
Oh, I've been here.
Wally.
Hey, what's happening? No, I've been here since the beginning. I was on the Facebook live feed, but because I'm not logged on through Facebook, it wouldn't let me do anything. So I just wrote Christiane and said, "Hey, give me the link."
God, you have a fuzzy face there, Wally.
Yeah,
That's
I know.
great. Anyway,
But yeah, I've been here since the beginning, so go ahead.
this is Aesthesia. So this is a very old one, and it's considered basal to that whole group of Monstosauria. So anyway, there's no bones in this one that are fused to the skull. You don't see any dermal bones, just as I showed you on that Varanus. And now let's see if I can get it to go forward. There, good. So now another one real quick. Outside of Helodermatidae, it's Gobiderma. Needless to say, it's found from the Gobi Desert of Mongolia. Beautiful skeleton. Again, typical Mark Norrell and other people are finding these complete specimens. Now look at the dermal bone. They're essentially knobs, if you will, domed. They're connected. They're relatively small, and they're all fused to the head. So this is a progression of what do I do with my dermal bone? If I don't want to be eaten, if I want to protect myself, I'm going to have a lot of this, and I'm going to fuse it. Okay, so we're going to see a progression. Needless to say, with this kind of a specimen, there's so much one can play with in terms of phylogenetic studies. We're not going to get into that. Your Heloderma from the essentially Eocene of France. So now we're seeing that it's not really just Utah, and it's not just, and as you can see below, in Wyoming, but all of Eurasia. So it's really a whole Arctic group of animals, lizards, that are developing through time more and more dermal bones and a source of venom to inject into things. So this is what your Heloderma looks like. They're kind of plate-like. They're not, they're rugose. They're definitely fused. Okay. But it's not what we're going to see in today's beaded lizard. Paraderma, Wyoming, Cretaceous again. We're looking at things that are beginning to look a little bit like what we were going to see in Heloderma. What I'm trying to do is I don't want you to remember this. I want you to see how it's evolving into what we see today as Heloderma. Realize that the whole group of Monstrosauria is really speaking Cretaceous and Paleogene. And then when we start getting into the Miocene on up, most of those are dying out. And we're at the very end of this whole group in terms of existence. Loasaurus, originally it was put into Heloderma by Gilmore in 28. So this has been known a long time, okay? It's Whitney and Aricarian, so it's 30 million, land mammal age, but about 30 million. Then Pregill, Greg Pregill and folks restudied it and found some more things. Again, you can see that they're dermal bones, they're fused to the head. This is the frontal, okay? So it's right in here. It's fused, but there's not a lot of organization in some ways. When they started looking at the teeth, here's a typical tooth. So in Loasaurus, here's a typical tooth. It's recurved, but you'll notice that there's a venom groove going from the root, the base, right on up to the tip. And then there's all these little phalanges coming off the side. And in many cases, there's a serration. There's a little bit of a serration on, this is Heloderma. Heloderma has the best groove, the biggest groove. It injects, if you will, or it actually really flows into the wound very nicely because it's just an open blood groove and it just shoots that venom right on in. It's not spitting it. It's not like many of the snakes. It's just flowing into it. Okay, so now what I want to do is kind of get into into the Neogene. So we're looking at Miocene on up. We're mainly looking at, so all the other things have died out for the most part, okay? Now we're looking at the genus Heloderma. And what I want to do is look at this very oldest one, which is right here. Here's today's Heloderma, okay? It speaks, doesn't really get into California, probably because of the laws. Nevada, certainly Arizona. Here's the Grand Canyon, so it gets into Arizona. Down to essentially Sinaloa, and then you start picking up a different species, Horridum, which they've now divided molecularly into a number of different species, okay? So we have this one, and then we have all these characters down here. This is where it occurs today. It speaks west. Here's the dividing mountain range, okay, the Sierra Occidental, and then the Oriental. They're not over here. They're not known out here. Yet we have this fossil here. And then we'll talk about these in turn. These are the localities. Don't necessarily really need to read them, but this is all that's known. Here's Loasaurus. Again, we're speaking Wyoming, okay, basically. Here's Heloderma. The fossil sites are very few, and the fossils within that are very, very few. Rich White helped basically in locating this one here. This is the only one that we've been able to take really to species, and we'll talk a little bit about that. So there's not a lot. We need to find more. What's important is that where we're finding them. So here's the oldest one, that number 9 on that map, Heloderma texana. It's a pygmy form. Well, I'm not going to.
Yeah, perfect.
Yeah, but anyway, that's life size, okay? So if you will, that shows you how big that specimen is. But you can see from the diagram that it has lots of dermal ossicles. They're knobby, dome-shaped things. It's critical now is it's not flat, it's now more of a dome. And there's a pattern to it, typically. You can usually tell a cranial one from a body one at this point. Here's a remnant of that tooth. Again, you see all these rills, and then there's that groove, but the top part is broken off on this one. But it's an itty bitty thing. Now, was that typical of all Heloderma then? Was it a little thing that began to get bigger, or is this just an aberrant one and we have a very biased sample from the Miocene? Don't know. Okay, but this is so far known as the earliest Heloderma. A Ricarian, okay, about 23 million, Big Bend, Texas area.
Hey, Jim.
Yeah.
With most of these specimens, it seems like they're actually good cranial material that's going along with the specimen, not just an isolated find of some osteoderms. And so I'm wondering if you think if a lot more fine scale screen washing was done, that we would actually find a lot more in their distribution, even though it might only be osteoderms.
Yeah, I think so. I think it's two things. One is the people who sort bone from sediments typically get trained in mammals. Nothing wrong with that. That's, and we're used to finding teeth in bone, and therefore that's the most critical thing to look at. Well, that's with mammals, and in reptiles, it's different things. And so I think we need to basically teach our picking and sorting folks, hey, there's a lot of skeleton to understand, and they all look different, even though early on you kind of get, well, it doesn't have teeth, so I'm not going to worry about it, And so that's certainly no cut against mammalogy side of it. It just means we need to branch out, and we do need to know everything when it comes to the skeleton, and we do need to sort bone after screen washing through micro mesh, by all means. Micro mesh. How are we doing for time? Okay.
We've got about 5 minutes before we hit into the questions.
Okay. Here's the gray fossil site. Da-da-da, you guys know where you are. You're right there. Bullseye. Arpita, that's your home. And here's what we're getting. Here's what Sandy recovered out of there. She's finding these little osteoderms. She goes, I think we got something new here. Well, here's the modern thing. So you can see how, or this is the gray fossil site. Here's the extant. So you can see that what we're getting is clearly Heloderma, and you can see the individual osteoderms. This is a skull that the skin's been flayed out, and again, I'm sorry, I don't want to really.
That's perfect.
Does that work? Can you see that? Okay. So, but you can see how it's very knobby and colored, but that won't preserve fossil-wise necessarily. But yeah, that was to me a real eye-opener to find it at the gray fossil site. And so, of course, Blaine and Wally and Sandy, we published this right off the bat. So the whole article was about these. And but it really opened up a lot of doors to understanding that whole group. So we've gone from that place. Now I want to shoot into a place in Arizona, 111 Ranch that Rich White, who's on the group here, is part of. And we published, we got actually, the sorting people did see a bone that had teeth. So that jumped out at them, which is great. The osteoderms are just bizarre enough that they kind of like, something's going on here, maybe I'll save that. But we need to start exposing people to all the variation to say, hey, we might have something else that's really bizarre. So anyway, in this case, you can get an idea of the venom groove. This little knob here, this is the right maxilla. This is part of the bone that forms the top of the face. And this would be where the nasal area is. And that little projection there immediately told us we have suspectum species, not horridum, okay? It's possible there's a paleo one that we don't have, but we were able to get it to species on this. Blancan in age, so it's a lot younger. So we published that just a little while ago, 5 years, I guess that's not a little while ago. Now, so we've gone from here. This is another little spot down here that's not well known. Here is the earliest one. We just looked at this one, which is within the realm. And then Nick Shaplesky at Oklahoma says, hey, I'm digging this site, not quite sure what the age is, probably Pleistocene, but I think I have, a Heloderma. And of course I'm going, oh, that's so cool. I'm expecting this, right? I'm expecting, oh, we got a beautiful fossil and it's going to have all kinds of stuff on it. No, it's not that. This is the biggest specimen. That's a millimeter. Okay, so what we have is a Heloderma living in Oklahoma that is being chowed down on probably by a ringtail cat, and they just chew everything up. So it's broken everything up. But he knew he had Heloderma because of that osteoderm. So then he wondered, well, I know skulls a little bit, maybe these are Heloderma too. So I got, some 150 specimens of stuff and then sorted out a few things. This is all part of the brain case. So if you're looking on this Varanid, okay, if you're looking at this Varanid, we're looking at the base part of the skull. All underneath here is what we're getting. So it's really itty bitty in this area here. And so just identifying this bone here took me, I don't know, 2 days to do. So it's been challenging. It'd been tempting to say, oh yeah, whatever, we got Heloderma, it's this. But we're getting some good stuff looking at the basal cranial area. So that's, we get to this point, you kind of go, okay, this is where they are today. What's going on here? We have this as, Miocene, Pliocene, and this is Miocene, and this is Miocene. This thing is retreating back to this point of today. What's causing that? Well, during the Pleistocene, Miocene through the Pliocene, we know climate's beginning to change, especially in the Pleistocene. And as we go through glacial, interglacial, glacial, interglacial, because we know in the Pleistocene there's 22 of these things, This thing is probably retreating and expanding, and it's moving across this area from, I don't want to say from here, but this whole range is contracting and expanding through these glacial, interglacial phases. What's important is to say, well, then why don't we have a good record out here? Well, if you look at the fossil record, it's rarely do they do that much paleoherpetology studies out there, but that's not totally true. Al Holman's done a lot out there, but more could be done, and micromesh screening again needs to be done. And a lot of times the fossil sites that are found, they're accented by the studies of mammals, which is great, fantastic stuff. And then materials being pulled out as, oh, I know this is a reptile and an amphibian, I'll give this to Al Holman or somebody else to look at. So there's already that selection bias occurring. And what we need to do is really start looking at all this stuff. So you need to go to these sites and say, well, let me look at all your unidentified material. Well, if we did that at Grace, I'd like, oh my God, I'm gonna die. I won't live that long because there's so much of it. So there are these sites that we need to start looking at the micro. And I'm ready to take questions.
All right, let's jump over to David.
Sure thing. Thanks a lot, Jim. We've got some questions already coming in from our audience. So before I start reading those, a reminder for everybody watching, now is the time. If you have questions, go ahead and put them in the Facebook comments of the video. And like I said before, if you can't do that on Facebook for any reason, feel free to send us a message on Gray Fossil Site's Twitter or Instagram. I'll be keeping an eye on them. This first question in the list here is about the osteoderms from Ethan, who asks, do we know much about the embryology of those dermal bones? I wonder, do they come from neural crest or mesoderm, or maybe different origins in different cases?
There is a study or two that show how they develop. And so what I've been able to do with Heloderma, both suspectum and horridum, which are the two living species, is get, hatchlings and little itty bitty ones on up to mom and dad, older ones. And with that, you can see that it forms as a nice little plate separate from the skull, and then it begins to fuse onto it and becomes more of a dome. Now, I don't know histology very well, so I can't tell you what layer that comes from, okay? But there is let me get this book here. If you want to know more about the living ones, get this thing. because what he's done, what this author has done is he gets into who's written what. And it's a fantastic book about the modern Heloderma. So if you want to know anything about the venom and the histology, this is where to start on that. But unfortunately, I don't know that stuff. I can just look at it morphologically and say, oh, well, when you get a little hatchling, it's not attached in its little plate. But then you get a little bit older one, then it begins to dome out and then attach itself. I hope that provides somewhat of an answer.
I put a link to that book in the Facebook comments as well, so anyone who wants to chase it down can go right ahead.
Let me put another one up there, David. Again, for those, let's see if this will, can you read that okay? This is an old work. It's a masterpiece. And this is—
What's the name of that one?
Hey, what?
What's the name of that one?
I got to read it. The Gila Monster and Its Allies, and it's by Bogart and Del Campo. And it's fantastic. They've reprinted it, but it's also something that if you want to know more about this group, you got to get this booklet too.
Very cool. Our next question. Early on, you were talking about the relatedness of Heloderma and where it fits within lizards, and you and Blaine were talking about the different hypotheses of how the lizard family tree comes together. And Gino has a question related to that. They ask, how well supported, in your opinion, is the Toxicophora clade hypothesis?
Yes. I don't know. I suspect it is, but I think, as you may be implying, I think we would need to take that node and then really peel it apart to find out really how good is that. I suspect it's good. I think, in phylogenetics, you'll create these nodes and they're a good node, but we don't know what to call it. So we just call it a node. Hey, and they give it a name sometimes. I suspect that group is good, but I can't. I'd have to sit down with that description and peel it apart. Good point, though. I mean, it needs to be done.
Right. And then there is actually, this is kind of a related question from Charlie, who asks, how complete is the fossil record of venom adaptations in Anguimorpha? Is venom ancestral to the group, or was it developed independently?
The development of venom has happened multiple times in all vertebrates, okay? And they're not all the same, other than you spell venom the same way. But when you start looking at the toxicology of it, they're all quite different. You can even see that within snakes, let alone all the other things. I mean, you can get it in shrews and things like that. Within Anguimorpha, it's with the early fossils, you have to look at, well, what do I see that says venom in the bone, in the tooth? And so we were looking a little bit at that with the teeth and the groove and all that sort of thing. Serrations, I pointed out serrations a couple times, and serrations do not dictate venom production. We see serrations developing in Mecasuchine crocodiles and other crocodiles. You see it in a variety of things. Dinosauria, various ones have serrations. I think even Tyrannosaurus rex has serration on a tooth. And of course, you're 7 tons. Why do you need serrations? You're probably big enough to do whatever the hell you want to, but they have serrations. But in the case of in Anguimorpha, the serrations on the edge of the tooth, and I might point out the edge of the tooth, there's a little flange that develops. Then the serrations are out on that, okay? And it probably helps the venom to get into the animal that it's chowing down on. But that morphology does not dictate venom. Just the grooves right now are dictating that. And all those little rills coming off the side of the tooth. Does that kind of answer it? If not, I can go more into it.
Sounds good to me. And I'll ask one more, and then we'll see if anyone in our, if Blaine has a question he wants to ask.
No, none for Blaine. No.
Maggie asks, how much do we know about osteoderm morphology during the Mesozoic or even Paleozoic?
Well, okay, Paleozoic, now you're going to shift to osteoderms in fish. And I don't do sushi, but there's a lot in placoderms, think about that. That's a dermal head, okay? So a lot has been done now. Histologically, I don't know how much they've done with, say, the Paleozoic stuff. Getting into the Mesozoic, we don't really see, I don't really see that much talked about, but I don't know the Dinosauria literature on that, and that would be neat to really know. I've just done, the squamate group, and seeing how much variation is developed just in the last, say, 100 million years within lepidosaurs, I would think that it's all over the place. There's probably really cool things to learn from all the different groups. That doesn't really answer your question, but there's a lot out there, including sushi.
Hey, Jim. We have one from Aaron Woodruff. You remember Aaron?
Oh, yeah.
He wonders how diverse were helodermatids and were there different morphotypes? So did they all look like what we see here, or did they have different morphologies?
Everybody's different. Every time you seem to find, when you're in the Cretaceous and then you're in the early Paleogene, whenever you find one of these rare specimens, it's different than the next one. And so that's why the phylogeny is all over the place, because there's, here's another one and it's similar, but it's about other little doohickeys. So now we rearrange the whole phylogeny, the whole clade. But there are some things that tighten it down to a monophyletic group, and a lot of that is the type of dermal ossicles, and then the venom grooves and the formation of the tooth, the way we've seen it, way I've shown it in the teeth. So there's again a lot more could be done with that, and I would hope that somebody would start looking at some of the, I would assume it'd be the smaller Dinosauria could actually have. I don't know why it wouldn't, but other, those animals are so many ways numerous and exotic that they're looking at the bigger picture of the skeleton, not necessarily the little tooth,
All right, other questions?
And we've got a question here from Mason who asks, in terms of Heloderma fossils in the eastern US, what aged sites would you expect them to be at? Would you expect it Miocene onwards or what?
Oh, good point. Well, of course, we know when you get in eastern US, finding Miocene is phenomenal anyway, right? You have Pipe Springs, and then you have, you could get it along the coast, I guess there could be more. I think I would want to search every Miocene site, any place, and just greenwash the pudding out of it, and then sort it with a real detailed critical eye under a microscope. This is not one of these things of, well, I look at it and I don't see anything. It's kind of like, yeah, okay, well, you're blind. So what we need is, we really need to get into using a microscope for this. And I think at that point, we're going to start finding it. Think about getting part of a tooth. If you found just part of a tooth, but it had that venom groove on it, you go, I know what I got. I got something that's within that within Monstosauria. So I think much more needs to be done in Florida, because that there's a lot of Miocene, even Oligocene material down there. But again, most people are not looking at this stuff. Now, Jason Bork is starting to look more and more into the late Oligocene material to see what stuff's down there. And there is, the article that I kind of referred to a little bit, the Florida material by Anjan Buller and Krista Smith, there is a lot of stuff down there. Boy, there's a whole career down there just looking at the lizards, let alone Monstosauria.
Chris Widga.
Yeah, so I'm kind of building off that question, Jim, but looking at this contraction of range through time, it's intriguing, and clearly, temperature is probably part of it. Climate's probably part of it. Are there other aspects of it that might start kind of parsing that out and make it more complicated? I mean, are there prey relationships? Are there predator relationships? Or precipitation? How does that change things? What is going on with that range dynamic?
No, that's a really cool thing, and I'm playing with that in my mind with this Oklahoma one, which we have articles in review. It's been reviewed, and I got to do some changing and send it back in. I think if we take the modern specimens and their critical issues of where they live, why they live, as the norm, then I would say temperature is very critical. And so if you travel east, that way's east, if you go east and it gets cold, you can die, you can go back west where it's warmer, or does the ground allow you to dig a hole and burrow down into it and then wait out until summertime, let's say. So are there different mechanisms with that? And that may be geography to a certain point, and then climate. How long does it stay cold? Now, I suspect the Oklahoma specimen, which was chewed up, I'm certain chewed up by a ringtail cat, which we found there in the fossil. We found a lot of that. It's a fissure fill, but there's a lot of bones in there, and a number of them are Basiliscus. I suspect it didn't, go tromping along going, oh, there's dinner on the hoof, and just go right on up and chow down on this Heloderma. It probably caught one that was an estivation, maybe a torpor of winter or something. Don't know, but that would be one way that a little carnivore like Basiliscus could jump on and grab a larger venomous animal. The one that we're looking at here in the picture, that's suspectum, and that's, they usually don't get, typically they're not much more than a foot and a half. As you get down into southern Arizona, down into Mexico and further south, they can be 3 feet long, 9 meters up in a tree. You kind of go, huh? I'm not used to that. I'm used to the thing that lives in, sand that's hot as hell and all that sort of thing. So there's a lot of variety there. I don't think we give this animal credit. And that's what I'm trying to play with, Chris, to figure out how is it fluctuating as it went east to west, or it was already east, now it's retreating and then retreating, and little by little, it's just where we see it today. What it's going to require, besides finding the fossils, is doing an accurate age of that deposit. And that's critical. It's not like, oh yeah, well that's Blancanen age, or yeah, that's Hemenfordian or something. It's, well, once you get into Pliocene, which phase do we have? Do we have a glacial or interglacial? That's, of course, your game a lot. And I think that's where we need to go.
All right, we are getting to the end here. Are there any last questions, David, that you want to toss in? No, Dave? All
Okay.
right.
Yes, I'm back. Hi.
Put you on the spot.
Sure thing. No, I forgot to unmute myself there.
Okay.
It's all right. I'm just the tech guy here. Here's a fun one to end on for you, Jim. Charlie asks, what made you specialize in squamates?
And that's Charlie Bruce, Jim.
Charlie Bruce. Hey, good. Thanks for asking a question. You're fired. Let's see. Well, growing up academically, working on my master's up at Tumamoc Hill, where most of the graduate students of Paul Martin worked on plants. And then there was a guy named Tom Van Devener. He said, well, there's lizards and snakes. And I was always interested in them, but I said, teach me. So we started working a lot with lizards and snakes, but I kept looking at, at the mammals. So I did mountain goats for a dissertation, along with lizards and plants and everything. It's all part of what Dick Mull says is know everything, but lizards are just cool, and the snakes are cool, and each one is its own problem. You can't take how you identify a snake and apply it to a lizard, because it ain't the same. And as Jasinski knows, it'll be different for the turtles. And we don't do fish and birds, talk to Steve Emsley and Dave Stedman. Lots of differences.
All right. Well, that will take us to the end of the broadcast. Thanks again, Jim, and thanks everybody for listening in.
Sure.
Thank
And
you.
Blaine, before we
Yep.
head out, we should mention that there will be a Paleo Talks next week, and then we're going to take a holiday break. So
Wow.
after that, we'll be back in 2021.
That's right. So stay tuned.
Thanks
Thanks,
everyone
folks.
for joining us.